Thank you guys all for being here. If you don't know me, I'm Ryan. I step in for a lot of clubs here on campus. I'm also working on my own little subset of a lot of clubs. I'll tell you more about that at the end. Today we are going to be talking about language models. And for you, I went ahead and built a very small language model totally from scratch in C. I trained it on Dr. Seuss. So we're going to get to see some really insane rhymes later down the road. I'm going to apologize once and only once. My voice is a little bit hoarse today. I'm going to keep the water close by and we should make it through. All right. And I went to the studio webpage. If you guys do want to tell the details at the top, I don't know if you can see it, but iHeartComputer.club/baby-ln. Or if you just go on iHeartComputer.club, you can navigate there by using the little projects tab. Awesome. So, demonstration goals. Obviously, we're going to talk about some language model fundamentals. We're going to walk through the architecture of my very simple model, just 2 layers, and some hidden memories. We'll talk about all that. We're going to discuss the limitations of our model, contrasted with some real large language models that you guys are probably familiar with working with. We're going to take a very brief look at the implementation. If we have more time, we'll do more. But quite honestly, we might get a little bit bogged down. The math isn't crazy, but if you're not familiar with C and C syntax, it's probably just not going to be that useful. Then we're going to look at some inputs. I have a series of pre-ran outputs and things. The model is really small, so I'll get just spits out a little bit of nonsense, but I went ahead and shared a couple that are really funny, so we'll read those. And also, I expect to hear lots of Dr. Seuss lines and things. I just thought they need good examples, and they're kind of fun. Right. All right, we have to do key terms. So you mentioned tokens earlier. Tokens, if we're talking about them strictly in real language models, they are sub-word strings. For our purposes, and I'm just going to use the words interchangeably, tokens and words are the same thing. In real life, if you're talking about a huge model, you could have words, a couple of words be a token. You could have part of a word be a token, or you could have the whole of one word be a token. For example, ing is often a token that is associated with something sense of being an ing. Don't ask me. Vocab is a list of all the tokens that the model has access to. It's been trained on. It understands, and I'm going to use that term loosely as well today. But it can also output them. The variable is just a numerical value stored by our model. When you hear about the size of models, you talk about parameters. They're really just some floating point values stored by the model that then, obviously we have a long list of parameters and they're stored on a piece of disk somewhere. And those are the trained values that the model is holding on to that actually give everything meaning. Context. Context is some set of tokens that we use in order to generate the next set of tokens. In our model, we're using what's called a bag of words. So that literally just means we take a bag of words, 5 words, more words not important, and we use those as a context. In real models, and we'll talk about this later, they use something called attention to dynamically create context. And that's one of the big separators here, but we'll get into it. The logic. This is kind of where it's going to get a little weird. This is a underlined wise, not a score for vocab words. And I'll take a brief detour and talk about the dot product here. But yeah, actually, this past week, I'm looking at a dot product. And this lovely graphic I made. Look at this. Wrote this up in paint. All right. So yeah, dot products measure how close 2 vectors are angle-wise, scaled by their magnitude. Just think about it today. Imagine that all the vectors, if you wear a ruler on them, they're just it ain't just 1 foot, 1 meter. I don't care, just 1. The dot product is 2 vectors coming in perpendicular directions to 0. If they point in the same direction, it'll be 1. That makes sense, right? Pretty intuitive. And so when we go back to logics, this is that score. How close these 2 vectors are is the logic value. And why that's important in a little while, but keep that in mind. And back here, a softmax. Softmax is a function that turns those logics into actual probabilities. So suppose we have 100 vectors that measure the closeness of 2 different vectors. The softmax function will turn this into a probability distribution. Relatively I'll show you more of that later. Loss, almost done here. Loss is how wrong the model is when comparing probabilities. Imagine that there's a target word. Suppose we have cat in the next one should be hat. The model will predict the probability, say it thinks hat is 60% likely the next word. That's wrong. The actual probability is 100%. So the loss would be the difference in between those things. We're going to use the negative logarithm of that value, not including y, but just to be rigorous. So if you've taken statistics, when you have a probability distribution, it's just choosing a random thing within that probability distribution. It's like if you've seen the Plinko balls, you drop one in, goes where it goes, and it's slightly random, but obviously heavily favored towards the middle. Temperature is the steepness of that probability distribution, and the Plinko line analogy kind of breaks down here if you think about it. But if the thing is real steep, that means the value right in the middle is much more likely. And if it's kind of flat, it means that the distribution is a little bit more spread out. It's more likely we'll get to those edges. And then finally, training is constantly running through this cycle and adjusting the parameters in order to reduce the loss and make better predictions. There we go. Let me take 1 second here. You got it. So, obviously now, what the values you can get. And so this is an awesome example. This is actually, I will share the code of this in a little bit with all of you. The material prediction engines. What these things are built for is gathering some piece of context and then calculating the probability of every single next word being the actual next word. And it picks that thing, goes for it. This is achieved by we do token embeddings, and so we attach numeric values and they'll be rank vector to one of these different words or tokens, and those will, in a very abstract way, encode a real meaning to those words. And so we'll get into that right now. Cool. Perfect. Yeah. So these are real embeddings in you can see these are just different random tokens and a bunch of nonsense values that don't make any sense to our human eyes. Well, this down here is not a real interpretation or anything that came from our model. This is kind of a clever way to think about these things. On each dimension of these, there's they can represent an actual human understandable feature. And so you can imagine the fish has a high value in the column that represents an animal or an ocean. Meanwhile, the really be in an ocean, but not now. That's starting to make sense. And we'll take a quick detour one more time and just talk about dimensions. You guys, it makes fundamental sense. If you have a one-dimensional vector, you can imagine on a number line. If you have a two-dimensional one, you can imagine it on kind of a coordinate two-plane graph. Three-dimensional, you can envision that. What does it look like, though, when we have an arbitrary number of dimensions? Right now. It doesn't matter, is my point. The geometry still works. We can spend in dot products, we can still in matrix multiplication. It just doesn't become really geometrical or understandable. It's where that kind of encoding meaning comes in. Each of these dimensions no longer represents X, Y, Z. This represents noun, thing, whatever. Come with an arbitrary list of meanings. And each of these tokens can kind of start to hang on to human meaning through its embeddings. If anyone is getting lost, please say so. I'm happy to take a break.
So basically, the closer it is to 1, it's a higher probability.
Exactly.
Closer to 0, then it's more of a answer.
And so, for the purpose of our model, we leave the maths and negative number being read. Thought about it as a function. We use the hyperbolic tangent to normalize them and squash those down. I'll talk about why later. But exactly, the value of 1 would be overlay maxed out on that feature, and negative 9 would be eliminated away from that feature. And so, yes, obviously, discovery, we don't directly translate. You might not be able to, even in really, really good models, you're going to put animal onto one of the embedding dimensions. But it's a clever way to think about it. And very interestingly, you might have heard of the king and queen example. You can do algebra on these vectors. right? So suppose that you have the vector that represents the word king, the vector that represents the word queen. If you subtract them, you get another vector. And that vector will, in some kind of weird way, exactly match the vector that represents men and this vector representing women, their subtraction. So you can kind of imagine that vector that is equivalent is sort of representing the axis that encodes for gender in these words. And so my funny example is me plus Christmas. Christmas is about equal to Grinch. And I built the two that like can do this. And it's a little shaky, but you can kind of get the okay. So I hope you guys like all the colors I picked. I made this in Google Slides. So we'll go through, this is what we call the word phase. What we're going to do is I'll walk you guys through this and we'll kind of see if we can pick it apart. This is going to assume a perfectly trained model from the start. Right? Imagine that this is the embedding table, and these on each of these axes, like this is a word, this is a word, this is a word, this is a word. And so these are all just assuming that they're correct for now. What we're going to do is we're going to grab the context. If you're familiar with Dr. Seuss, you'll know Ben's, Bings, boom. That's harder than it looks. So we're going to grab the four vectors that encode the meaning for those four words, and we just sum them up. We're going to get the sum of those four words. We're also going to go ahead and add the biases. There's a bias table that we use in order to kind of keep a good track. I'll show you the code for exactly how this happens, but we track just how common a certain word is so that we can add higher bias to words that we see often. Anyway, we're going to add every single value, like this plus this plus this plus this will be equal to this. And we'll go through that and do it in every row. And we get a hidden vector. And what we call this is the hidden representation. Now, that vector should hopefully map to a vector in the output projection, which is another assumed perfectly trained. And what should be, if you can imagine this one is this way, it'll be this way. Not super important. But you can imagine that this output projection is full of vectors which also map to words. And it takes these features, which we've gotten from the addition of all these things, and it puts them in, we can match them up over there. What we do is we take the dot product here and we use this. We have a hidden vector. We use the dot product, which, if you remember, brings a similarity of two vectors. And so you check this with all of these, and each of these represents a word once again. I'm going to lose people here. Kyle, you got that? Kyle got it. Everyone gets it. Stop me, though. Hopefully that makes sense. What this will produce is these logits, as I said earlier. Those are unnormalized, random kind of seeming values, but they compare the similarities scaled by the magnitude of these vectors of each word in the output to the hidden representation of the context input. Well, kind of adds. Now, this is really cool. We take this and we put it through that softmax function I mentioned earlier, which turns these kind of random seeming numbers into a probability distribution that we can fit on one of those nice curves. Pretty cool. And now, once we have this, we can say, all right, Fox is the most probable word. And so there's more to it when we properly sample these things, but we'll probably end up picking Fox as the next word. And I don't know if that's actually correct. Ben's broom fox. The example's not important. But that is the full maps of the notes. And you can see in this one, it's only two layers. In UMRs, there'll be potentially many more. And at every step, we'll observe a hidden representation, take the dot products with the next layer, build another, something like a logits that can become a probability distribution. This is the sort of workings of once we have a training model, this is how we produce next words. Please. How do I get through the output projection? So the output projection, in our case, for right now, we're just assuming this is perfectly trained. Like words, this whole vector is represented by a word, this whole vector is represented by a word. And so once again, we produce this hidden vector from a context of, say 4 words, and then we use that to map to a word over here. Oh, this was moving dot product. That's another, that has nothing to do with the first, not necessarily.
Would this be like a sample, like similar to like linear regression?
We will get, so yes, there is regression that will come later on when we do our backpropagation.
So every alpha token has its own probability distribution.
Every output token, is that nice? So every token, every possible token will be in the probability distribution. So if you can add 100 words, these are the most probable 5, but every time you do it, every one of 100 words is in there with some probability on it. And so we produce an entire new vector of probabilities. An example from that. There we go. If you don't get it, please say so, because I'll keep yammering forever. All right, assume I'm perfect. Okay, training gets a little bit weird. So training starts right where the forward pass ends. And so interestingly, when we go to train, we're actually doing the same computation initially that we would do to generate. What we're gonna do is we're gonna just pick a random place in our context. Like we have a training, what we call a corpus, and a corpus is just, it gotta be a single long text document. It can be a sample of many pieces of text. In our case, it's about 30 kilobytes of Dr. Seuss that I very legally obtained from the internet. And anyway, we're going to pick a random place in that corpus. We'll build a context. And so Fox, or whatever it was in the first case. Well, that's it. I'm not saying it yet. Whatever. But we do that, we'll build the context, we'll run through it. Now, what happens is, since we're doing the corpus, we actually know what the next word should be. And we can compare that to what the model predicted. So the model said that the word was fox. We know that that's not the case. We know the correct word was box. Now, what we can say is the probability should have been 100%. If we can assume this model was perfectly good, we can assume that box's probability is 100%. Everything else should be 0. So it gives us the ability to say, all right, it was the underpredicted box, so add something to every single one of its features, and we overpredicted everything else, so subtract something from every single one of its features. And now that number we subtract is uniform across them all, at least in my very simple model. And it's just, the number itself we can look into later, but there's a running rate, which is just some small floating point value that I decide at whatever time. And then that's multiplied by exactly how wrong it was. So if it was really pretty wrong, it's going to adjust everybody quite drastically. But if it was on a little bit, it's going to adjust everybody just a little bit. Now, also on this layer, and so this is the output projection that gets corrected. The embedding table itself, now we're going to take this hidden vector, which, remember, kind of would encode the features of all the context words. Anything we know that, we know what box's hidden vector should look like. And so, what I didn't say, some of these features were too strong and some of these features were too weak. And so once again, we'll grab the learning rate and we'll grab, exactly how long it was, and we'll subtract a uniform value across all of the vectors in the embedding table. And so we run this, a couple million times. Let me say, this is a graph of my model in action. You can see this starts quite high, and I think, interestingly, and I don't understand the geometry of this off the top of my head, I think that's about 6.8, which is like the negative log of exactly how many words are in the corpus, which I'm going to look into at some point. It's an interesting one. But you can see that this thing, as it approaches 0, the guesses are getting better. And this is calculated from the logarithm of how wrong the prediction was. And so you can imagine if the prediction hits, what would it be? The prediction, when it predicts the right word, it's 100% or 1, that this will get to 0. And you can kind of see it's kind of bottom out here. This is after a million iterations. And if I had a graph of 5 million, you can see that it tops off pretty hard. Because in reality, there's no exact correct word. You can imagine that I could use a lot of different words in a lot of different sentences and still be technically correct. So you kind of have to play that game with where do you want to stop training, where is it good enough? And where is it just going to be really doing nothing but confusing itself. You get so far? Okay. So you really get look at that. So our model was a little bit limited. This was one output that I got. It just said feast like 150 times. I don't even know why I did that, but you have to imagine something was slightly off. Basically, some of the limitations there. But you provide short-term memory only. This one is working with a 4-word context. I believe maybe this guy was trained with more. This got an 8-token context. But even 8 tokens, and they're just straight from the string, that's not very much. So as soon as it's lost those 8 tokens, it can say the exact same thing and have no idea. It obviously can't stay on a certain task or maintain certain themes, or stay on a certain writing style. Like you can ask some big models like ChatGPT to do. Word order doesn't matter. This is a bag of words implementation, and so the context is a bag of words. I could flip them around; it doesn't matter. It ended up whether it was pop on pop is the same as pop on hop. It looks exactly the same to the model, unfortunately. Common words end up being too common. This is an interesting factor because of those bias tables that we used. Basically, every time we hit the word that, we just add a little bit to the embedding for the. And so over time, those super common words get super bumped up in the bias, and the model doesn't have a concept of I just said this, or the word does not fit here. So unfortunately, it ends up saying some common words, some common phrases more often than it should. When finally, at this scale, the model is only able to learn basic patterns. It's not really picking up this very small one, which is, I think, in total about 2 megabytes. Not going to be able to actually pick up on grammar rules or sentence structure. You can do sentence structure, but no grammar rules. It doesn't actually understand any ideas, rules, facts about anything. However, despite this, it does learn some decent sentence structure. It can, in certain circumstances, completely quote Dr. Seuss without that being hard-coded at all. And it can kind of come up with some interesting, slightly funny outputs. If anyone wants me to read this, I do not like them in a box. I do not like them in a box. I do not like them anywhere. I do not like them, Sam, I am. I do put you in the realms, or live in us cooking out in the rain, back in the train, and we fish are blue fish, the blue tree should shake to hop. I do not look like. I do not like them, Sam, I am. That was him, not me. That's John. So, another thing to take us from here to real life deep language model. This is conceptually right on the money. We're doing everything we're doing, except for one thing. Attention is a big topic, and if you're familiar with the paper, attention only is a little attention. It's very famous, and I have it linked on the sources for this. But attention is a mechanism I mentioned earlier, and it allows the model to actually create its own context and dynamically hold on to pieces of it that are important. They also just have much larger contexts. Yeah, I could train this thing with a 32 token context, but I'm not sure how much we would gain from it. Now, the models today are able to do this because they take advantage of transformers. Transformers are basically big structures that allow us to put these things in huge matrices and just perform optimized multiplication on them. If you're familiar with matrix multiplication, it's just doing a bunch of dot products over and over again, which is an operation the GPU is super, advantaged to do. And you can also do it one by one, individually, concurrently. It was only on the CPU, so I can try to fit million iterations, but it takes like an hour. We realized, ChatGPT, when they're training it, is doing about 1 million operations a minute, and then they run it for a couple months. So I'm just not at the scale. I sit here, all as a vocab of 1,000 words. GPT-2 has 50,000. And that was a model from quite a long time ago. Now they have, obviously every emoji in the book. They also have every word, hundreds of languages. They're getting pretty big, and we just can't match it.
Is there any randomness of collection, or is it always choosing the highest token?
It's totally random. Because what we're doing, I can show you actually over here. I have something. Here we go. We're starting from a probability distribution. So you can imagine words on the axis down here. Now, I'm going to drop a Plinko ball right here. And I can see he's going to land on one word. Most likely, it'll be one right near the center. But who knows? It's so at some point, there'll be a random seed that you give to the computer when you say, when you call the C function for random, is not totally random. It is a little bit random.
So that mechanism give the model more generative and think.
Yes. And so what we're going to get into here in a little bit. But this low temperature versus high temperature, this is where the Plinko ball analogy breaks down. But when this is room temperature, the word right in the middle has a much higher probability, and we can adjust that and say we want high temperature. And at that point, this word and this word are not so far apart. It's really to kind of spread out inside the probability and get more random. If you've ever played with like any of the OpenAI APIs, you can adjust the temperature when you send a request. And so, if you get a temperature like 0.8, 0.9, another crazy does if you use like 0.1, it's going to always basically say the most likely thing. So yeah, GPT-4 I did math 20 million times bigger than the one that I produced, and it also takes advantage of some other cute optimizations that I didn't have the time to do real quick. So you can imagine, with the time I had, we did it very best. This is mathematically sound, but it's just not quite at the scale. So we can look at the implementation kind of briefly. And this can actually, I'll talk about some of the current events as we do this. You can see this is a corpus structure. It doesn't really matter if you understand the syntax. All the is we're keeping track of the valuable vocabulary. We're keeping a track of all the IDs of each vocabulary word. So you can imagine vocab in to the model, everyone has like 0, 1, 2, 3, 4. Just because it doesn't bound work with actual strings. As far as the model itself, these 4 values right here are really what makes the model. These though are just a single number, but we store the embedding matrix, the embedding weights, and the output matrix, the output projection matrix, and the output projection weights. And the addition of these 4 values times the size of a floating point, which is 4 bytes, will get us to our number to the size of the model, which is about 2 megabytes. So, now, so I'm not going to bog you guys down with the implementation of these, but an interesting note, when we call these functions like I wrote in real production, if you're running why RAM has gotten so expensive, when we have to load the model, we got to bring it into either RAM or VRAM, which is just RAM for the graphics card. And when I have a model that's 2 megabytes, there's no problem at all. I love that. How big is Quentin?
4 gigs. Why quantized versions?
With quantized version, if you want like a production, like a 1 Ramos, you're talking like 400 or 500 gigs. And so when you play this, you're in trouble because first of all, your graphics card, we can handle that, but it's probably not got enough VRAM or RAM in the first place. So it's got to be either you got to get more RAM, and so that's what these huge data centers do. They just buy more RAM, or you have to load parts of the model at a time and unload them. That gets to be a mess. So you can think this function right here, we're having for why everything is so expensive. So now this is the code behind the fluid phase. You can see this is simple enough if you let's see. Everything we're doing is we're looking for the context words and then add every single element, just element, and we get one single hidden representation. And we also use the hyperbolic tangent, so we can just squash those values down into a range between -1 and 1. And down here, I should have a word about that. Perfect. Look at this. So suppose I get a really high value. We call that feature saturated. And so what's nice about the hyperbolic tangent is as you push further this way, it's doing very little. So we can always say, like, if you have the word fish, the word animal, like the feature for animal, is probably pretty maxed out. So adding more to it is really not going to do anything, and we don't have to worry about doing expensive math. And this is the softmax. If you're interested in it, all it's doing is converting everything to probabilities as we go. And you can see we call that here. Having done this right here just does the dot product of every single list the hidden representation, so we can get that Logits array, and then softmax, of course. If anyone wants to look at this code further, I encourage you to do so, and this whole thing will be obviously shared and posted and whatever. So now the generation is, all we do is we just call a sample function across that vocabulary and the probabilities, and we just type the word, slide the context over. So the cat in the, we chose that hat was the next word. That'll be cat in the hat, and we'll guess on the next word. And that's how I keep this nice and simple. This is the piece that does that propagation. So if you're interested in gradient math, I will encourage you to read this, but I don't think it's useful for me to go through it on a good time. This is a great website from Stanford for one of their CS courses. I think it's actually pretty good mostly to image generation, but I read it and got some useful stuff out of this and managed to write this thing. So I encourage you all to read it if you're interested. But this thing's a mess. I'm not going to touch it. I think it's better if I just keep that back propagation kind of abstract. So, you know how to come up here and read these? All right, now stand up. Yes. Yeah, stand up. I'm just gonna read this little guy. The entire paragraph. I was going to read to you and train to 1 million steps with a 0.7, so that's relatively high temperature, and a 4 token context. The prompt is, I do not like green eggs and ham. Finish the sentence, Kyle.
I do not like them in a house, and I will eat them in a box, and I will eat them with a fox. I will not eat them on a train, not in a car. You let me be, I would not, could not in a car. You must be, I do not like them, Sam. If you see not, I like them here, and they say I don't choose to go there.
See, how fun is that? 200 whole token. So that's what all that math gets you. See, this is not a terrible, but interestingly, I'm not making better than the rest of them. But if you get on these, they're funny because as I lower the temperature or increase the training steps, it gets closer and closer to just directly quoting Dr. Seuss. When you read this one, there's relatively low temperature and 5 million training steps, which is way too much. He directly quotes one places you'll go. And then at some point halfway through, he does switch. I'm making W as a this next example. If anyone knows the can that silence. Come on. And the same with the next one with the 0.2 temperature. This is quoting some exact story of the cat in the hat by Dr. Seuss. The sun, the rat shadows too wet to play with, so sat in the house, and let so wet did I sat. There was sour and reset. He's quoting exactly, which is very interesting behavior for such a small model. And it can directly recite back to us some lines of Dr. Seuss, at least for 200 tokens. I could probably do it for more. So I would call that pretty successful. Now, I also wrote a small answer tokenizer that also includes punctuation and white spaces. This sort of would try to work more, the actual poetry that it's supposed to be written in. And this is funny because the use of punctuation is on average, it's pretty good. You can see some sentences where we have periods right in the middle, but on average, we're getting about 4 to 8 rows in a line, and easy punctuation error at the end. And you notice it likes to do this space and then a nice on more space. It's not going for 10 spaces in a row or anything weird like that. So that's some interesting behavior. This is a hardly trained model with a high temperature that I just happened to get to give me a nice output. Just a funny thing. And then I think this one is completely untrained. So I'm not even make an attempt to read it. But as you can see, as by am isn't that 0.7 high. It's not this is completely nonsensical. And so go from this to this, I would say it is kind of a successful attempt at proving I did train this thing to produce somewhat readable text and at the very least predict a decent enough next word. So that's all I got. Please.
You mentioned something about overtraining.
Overtraining, yes. So that's where I'm talking about, like, up here. At some point, it's just going to directly create the training corpus nonstop. And like I said, if you were to watch this as it went, it would get a loss down to 0.01. It would just bounce 0.015, 0.095, 0.015. And we just kind of bounce up and down and never really improve because it's never going to be perfect.
Couple of questions.
Sure.
What is the size of your training set?
The size of the training set was about 30 kilobytes of Dr. Seuss. We could scroll through it right now, but it's literally just a couple of, random books I'm able to find online.
Oh,
So
the other question was, what was a mass function you think $800?
So, one more time?
On your back propagation, I was just wondering what loss function.
So, I'll show you exactly which loss function I want. Sorry. There we go. So, I'm going to start with logarithm. And my last function. So, yeah, this is exactly what we're doing. We're just taking the negative log of the probability. And so the reason I'm doing that is, the negative is because we technically want the inverse of this. And so with logarithm, it comes to the front. But as the target probability approaches 1, which would be 100%, we perfectly predicted the next word, the log should return 0. And so we slowly approach that, as you can kind of imagine you saw in the graph. Anything else? Are you convinced? Well, that's all I've got. Please feel free to read this code. It's all posted online. Like I was saying before, this is going to Alport's on Discord. That's my Discord. If you are interested in hearing more from me and possibly coming out presenting your own stuff, we'd have a cool little crew of people who are building interesting projects and are happy to talk about them all the time. Please do. We'll be having some fun. You'll probably see me again. Thanks, guys.